Accurate boundary condition for moving least squares material point method using augmented grid points. This research is co-authored by Nobuyuki Umetani. Our research target is a simulation of deformable objects. This kind of simulation have been widely used in the movie industry and computer games. So many researchers have been studying this field eagerly for a long time. Material point method, so-called MPM, is a popular technique for robustly simulating various deformable objects like snow, sand, and jelly. However, MPM has some problem about its accuracy. So our motivation is to make MPM simulation more accurate. This is the result preview of our research. The naive MPM suffers from inaccurate boundary condition, resulting in particles penetrating to the wall boundary. On the other hand, our technique accurately handles the boundary and prevents particles from penetrating. From here, I'll show you the basis of MPM. MPM solves the governing equation with both particles and the grid to take advantages of the two domains. For example, a particle domain has a mass conservation property and can accurately handle advection. On the other hand, grid domain has an obvious adjacency information and is easy to parallelize. During the simulation process, MPM switches the two domains by interpolation. Let's see how the interpolation works for MPM in detail. In the domain switching phase from grid to particle, MPM performs an interpolation of velocity. And this interpolation is our main interest. Here, grid point velocities are pre-computed by solving a governing equation, and then interpolate to the particle velocity. The referenced grid points are limited to the 3x3 grid velocities to make the simulation fast. However, as I showed in the result preview, this interpolation scheme has a drawback that particles are penetrating to a wall boundary. Let me show you what's happening here. In the naive MPM, grid points velocities are set to be 0 if they are inside a wall. And the particle references the neighboring 3x3 grid points whether they are inside a wall or not. Although the particle's velocity should also be 0 on the boundary, it is often largely affected by non-zero velocity grid points. Therefore, the particle's velocity becomes non-zero and penetrates to the wall boundary. There is a previous method tries to overcome this drawback. This method extends the MPM to work on an adaptive resolution grid. It assigns a finer grid for the area around the boundary and a coarser grid for the internal area. Because the size of the interpolation kernel becomes smaller on the finer grid, particles penetrating problem is alleviated. However, it is still computationally expensive and complicated to implement. The second previous method is compatible particle in cell method, so-called CPIC. This method succeeded in two-way coupling with rigid body dynamics. In this method, ad hoc repulsion force is applied for a penetrating particle. The direction of this force is perpendicular to the wall, and its magnitude depends on the penetration depth. Although this treatment works well in some degree, its dynamics is beyond the MLS framework. Next, I will show you the overview of the interpolation scheme named Moving Least Squares, so-called MLS. MLS optimizes the fitting function by minimizing weighted least squares. Here, we want to estimate the value at x hat by fitting a linear function to the data point drawn as breakpoints. In this interpolation, a weight is assigned to each data point depending on the distance from the query point to the data point. The weight values are represented as the color depth in the left figure. By minimizing the summation of weighted least squares, the fitting is completed. Then we get the interpolated value as the point on the fitting function. This animation illustrates the interpolation process at many query points. The moving line represents a fitting function at each query point, and the moving green point and the line represent the interpolated value. So we get the interpolated curve like this. That's it for the overview of MLS. Up to this point, I have shown the basis and the drawback of MLS NPM. From here, I will introduce our method. Before introducing our method, let's see the naive interpolation around the wall. The estimated value at the wall is interpolated like this figure by MLS interpolation. Although the value should be 0 at the wall, it is not 0. This is because there is no grid point on the boundary and the fitting is affected by the linear inner grid points. To make the interpolated value 0, we put an additional grid point on the boundary, as drawn as blue points, and ignore any grid point inside the wall. By this treatment, the interpolated value becomes much closer to 0 at the wall. As you can see from the figure on the right side, the estimated value is strongly affected by the additional grid point and is no longer affected by the inner grid point. This figure illustrates the interpolated curves of each interpolation scheme. Our interpolation makes the field almost linear around the wall. This is the core novelty of our method. To extend to 2D, we put additional points on a boundary with the same interval as the grid cell size. However, after assigning additional points on the boundary, some of the boundary points are too close to the existing regular grid points. Such close points make the simulation unstable. Furthermore, when the regular grid point is on the intermediate of two boundary grid points, particles are likely to penetrate around that regular grid point. So we ignore those regular grid points near the boundary if its distance from the boundary is smaller than a threshold delta, even if it is on the fluid domain. We set delta to be 1/3 of the regular grid cell size. So this is the final form of interpolation scheme. The red and the blue points are counted for the interpolation. Let's see the simulation result. The left side is the naive MLS NPM, and the right is ours. Although the naive one suffers from the penetrating problem, ours can accurately handle the boundary without penetration. This is the case of circular boundary. Our method works correctly, even if the boundary is curved. Because NPM is a general framework for deformable object simulation, we can simulate other types of material, like fluid with full slip boundary. Hyperelastics, and plastic material, like snow. As for the performance, our method takes more time for boundary point searching and MLS fitting. As a whole, our method is about 1.5 times slower than the naive implementation. This is because boundary grid points are distributed irregularly, and MLS fitting becomes complicated for such data points. However, in this comparison, Point searching in our method is done by brute force searching. So we can make this process fast by introducing spatial hashing, like KD-tree. This is one of the future works of this research. Before showing you the comparison of the interpolation quality, let me give you the desired property of viscous fluid with non-slip boundary condition. The first case is fluid flowing down on a plate. It is known that the Navier-Stokes equation takes quadratic profile, especially the velocity changes linearly around the ball. The second case is fluid flowing through a tube. The laminar fluid solution called Poisson takes quadratic profile, where the velocity changes linearly around the ball. Therefore, we want our method to accurately handle the linear field around the ball. So, this is the experiment for comparing the interpolation quality. We chose the distance field for comparison because it is also linear around the ball. In this experiment, the correct solution of the distance field is set to the grid points, and their values are interpolated to the wall domain to reconstruct the ground truth. As you can see from the naive one, there is an influence from interior points going through the boundary, while in ours, there is no such problem, and the distance field seems to be linear around the wall. Finally, let me summarize today's presentation. The key idea of our method is introducing boundary grid nodes for better boundary representation, and it enables us to avoid problem of particles penetrating walls. As for the future work, two-way coupling with rigid body dynamics is one of interesting directions. And for extension to 3D, the reasonable way is to uniformly distribute particles on the surface using Poisson disk sampling, and then apply our interpolation scheme. Finally, we can accelerate the interpolation by introducing spatial hashing.